Today we are going to be talking about sequences and sigma notation. By the end of this video, you will be able to recognize sequences and write a rule to describe it. You should be able to calculate factorials, and you should be able to evaluate sigma notation. First, a sequence is a list of numbers, typically written a sub 1, a sub 2, a sub 3, all the way to a sub n. This means we have the first term, the second term, the third term, the nth term in our sequence. For the first problem here, we want to find the first four terms of each sequence. Generally, a rule for a sequence is written as a function. This a sub n here means the nth term is given by this formula. So if you want to find the first term, you just plug in 1 for n. If you want to find the 700th term, you plug in 700 for n. So to find the first four terms of each sequence, we are going to plug in 1, 2, 3, and 4 for n. So if we plug in 1 for n, we have 3 minus 2, which is 1. If we plug in 2 for n, we have 6 minus 2, which is 4. If we plug in 3 for n, we have 9 minus 2, which is 7. And if we plug in 4 for n, we have 12 minus 2, which is 10. So the first four numbers in this sequence are 1, 4, 7, and 10. If we look at our next equation, this one is a little bit more complicated. We have a sub n is equal to negative 1 to the n over 2n minus 1. Anytime you see negative 1 to the n in a formula, that means that the terms are going to alternate between positive and negative. So if we plug in 1 for n into the numerator, we're going to get negative 1. If we plug in 1 for n in the denominator, we're going to get 1. If we plug in 2, we get positive 1 over 3. If we plug in 3, we get negative 1 over 5. And if we plug in 4, we get positive 1 over 7. So you can see here that the odd terms are negative and the even terms are positive. Our third example is a piecewise defined sequence. You have learned about piecewise functions in the past. We have two different rules that apply for different values of n. So if n is odd, meaning the first, third, fifth, seventh terms, you are going to follow this rule, 1 over n. And if n is even, so the second, fourth, sixth, eighth, etc. terms, are going to follow this rule, 3 times n. So to find the first term, 1 is an odd number, so I'm going to use the second formula, which is just 1 over n. So 1 over 1 is 1. To find the second term, I plug in 2 for n. So since 2 is even, I'm going to look at the first line. So I have 3 times 2, which is 6. To find the third term, 3 is odd, so I'm going to look at the second line. So I have 1 over 3. And then for the fourth term, 4 is even, so I'm going to look back at the first line, and I get 12. So here we essentially have two different patterns that are alternating. Next, we want to look at writing an expression for the nth term of each sequence. So we are doing the reverse of what we did on the previous examples. We are given a list of numbers. We need to write the rule or the equation or the expression for the nth term. So first, we have 1, 3, 5, 7. It's frequently helpful to look and see if you are adding a specific number or multiplying by a specific number. So if we look here, we are adding 2 adding 2, and adding 2. Since we are adding the same number every time, this is actually an arithmetic sequence, which is a specific type of sequence that we will talk about more in a future tutorial. So, when we are trying to write our expression for the nth term, we have a sub n, or the nth term, is equal to, and then we need to find our expression. So, when we plug in 1 for n, we need to get 1 as our answer. When we plug in 2 for n, meaning the second term, we should get 3 as our answer. So we end up with 2n minus 1 as our expression. And we can double check this. 2 times 1 minus 1 is 1, 2 times 2 minus 1 is 3, 2 times 3 minus 1 is 5, 2 times 4 minus 1 is 7. If we look at our second example, we have 2, 5, 10, 17, 26. If we look and see what we're adding 3, then adding 5, adding 7, adding 9. So this is not going to be an arithmetic sequence. This is actually going to involve perfect square. And let me show you how I know that. If I start with a 1 by 1 square, I have 1. If I want to make the next larger square, which would be a 2 by 2 square, I am adding 3 squares. To make the next larger square, which is a 3 by 3 square, I'm actually adding 5 squares. Add 7 squares to make the next largest square, which is a 4 by 4 square. So I added 3, then I added 5, then I added 7. So anytime you are adding consecutive odd numbers in a sequence, that's a clue that you are going to be looking for perfect squares. So if we think about our perfect squares, that's 1, 4, 9, 16, 25. All of these numbers that we have are one more than the perfect squares. So our expression is going to be a sub n equals n squared plus 1. Now, our third example here, we have 1, 1, 2, 3, 5, 8, 13, 21. This is a special type of sequence. This is actually called the Fibonacci sequence. To generate this sequence, you take the first two numbers, you add them together, that will give you the third number. Then you take the second and third numbers, add them together, that gives you the fourth number. Add the third and fourth numbers together, that gives you the fifth number. And you continue. It would be very difficult to write an expression the way that we wrote it for the first two examples for this sequence. So there is another way that we can write the rule for a sequence, and that is using a recursive definition. So this is the Fibonacci sequence, and we are going to define this recursively. To write a recursive definition, you need to give a starting value, and then you can give a rule in terms of what to do with the previous number. So, our first term is 1. Our second term is also 1. to find every term after that, you are going to take the previous two numbers and add them together as a sub n minus 1 plus a sub n minus 2. This means if I'm trying to find the third term, I'm going to take the second term and the first term and add them together. So all of this together gives us a recursive definition for the Fibonacci sequence. Next, we need to talk about factorials. N exclamation point is read n factorial, and that means you are going to take every number starting with n and then decreasing by 1 and multiply them together. So we can write this out as n times n minus 1 times n minus 2 times n minus 3 times 3 times 2 times 1. You multiply all those numbers together, and that gives you n factorial. It is important to note that 0 factorial and 1 factorial are both equal to 1. If you're trying to find the factorial symbol in your calculator, if you go to Math, go over to Prob, and click number 4, that will give you the factorial function. So here we want to evaluate some factorials. First we have 5 factorial. Well, that means we have 5 times 4 times 3 times 2 times 1, which if you multiply all that together, you get 120. If you're looking in the calculator, you can check that by clicking 5, then Math, Prob, 4, and you get 120. Next, we have 8 factorial over 2 factorial times 6 factorial. Yes, you can type this in the calculator, but I want to make sure we understand how to simplify this without a calculator. So, 8 factorial is 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1, which is just 6 factorial. Since we are multiplying, we can cancel the 6 factorials, and we are left with 8 times 7 over 2 times 1, which is 56 over 2, or 28. Our last example here, we have x factorial over x minus 1 factorial. Clearly, you cannot type this in the calculator because it has x's. So, x factorial is x times x minus 1 times x minus 2 times x minus 3, etc. X minus 1 factorial is x minus 1 times x minus 2 times x minus 3, etc. So we can cancel out the x minus 1s, x minus 2s, x minus 3s, and everything that comes after that. And we are just left with x. Next, we're going to take a look at sigma notation. Sigma is a Greek letter that is used in math to represent sums. Sum meaning we are adding a bunch of things together. You could also see summation or the word series. All of these refer to adding a bunch of numbers together. So for sigma notation, this a sub k will be an expression. k equals 1 at the bottom of the sigma tells you the first number to plug in for k. Whatever the number is at the top tells you the last number to plug in for k. So if we look at a couple of examples, first we have sigma of k equals 3 to 6 of 1 plus k squared. So that means that we want to plug in 3, 4, 5, and stop at 6. So if I plug 3 into this expression, 1 plus 3 squared gives me 10. If I plug in 4, I get 17. If I plug in 5, I get 26. And if I plug in 6, I get 37. We need to add these numbers together, and we get 90. And that's it. You just plug in several numbers into the expression and add together the resulting terms. Let's look at a couple more examples. Next, we have k equals 0 to 8. We are adding 1 over k factorial. Well, let's go ahead and write this out. We're starting with 0, so you have 1 over 0 factorial plus 1 over 1 factorial, 1 over 2 factorial, 1 over 3 factorial. We're going to keep going until we have 1 over 8 factorial. Since we have factorials, we're probably going to need some help from the calculator. 1 over 0 factorial is just 1. 1 over 1 factorial is 1. 1 over 2 factorial is 1/2. 1 over 3 factorial is 1/6. And we keep going until we have 1 over 8 factorial, which is 1 over 40,320. If you add all of these numbers up in the calculator, you get approximately 2.718. You might notice that that's essentially what E is. If we had changed this summation so we had k equals 0 to infinity of 1 over k factorial, that is equal to E. Lastly, we have an infinite sum here. We have the sum of n equals 1 to infinity of 3 over 10 to the n. So if we start by plugging in 1, we get 3 over 10. If we plug in 2, we get 3 over 100. If we plug in 3, we get 3 over 1,000. If we plug in 4, we get 3 over 10,000. And we will keep going forever. If we change these all to decimals, we have 0.3 plus 0.03 plus 0.003 plus 0.0003, which gives us 0.3333. And we continue on forever, which is 1/3. This last summation brings us to an interesting idea in mathematics. The question is, does 0.9 repeating equal 1? Well, this summation would lead us to believe so. If I had changed the 3 in the numerator to a 9, would that equal 1? If 0.3 repeating equals 1/3, and I multiply by 3, then I get 0.9 repeating is equal to 1. Let's look at another proof to show that 0.9 repeating does in fact equal 1. So I'm going to let x equal 0.9 repeating. Then that means that 10x is equal to 9.9 repeating. I can split this up so that 10x is 9x plus x. On the right side of our equation is going to be 9 plus x, because we said x was 0.9 repeating. If I subtract x from both sides, I end up with 9x equals 9, so x equals 1. Therefore, 0.9 repeating is equal to 1. If you do not accept this proof, we can discuss it more in class.